Um, so let's start for today. So today's class we will try to um, so we will so we started yesterday we started on duality. Okay, so we started on this topic, and so today's class I will be trying to complete all the discussion I want on this topic on duality and try to complete some of the discussions from yesterday. Okay, so I want to start by recapping a little bit from yesterday. Uh, what we did, uh, we essentially, I derived for you yesterday a dual problem from a linear program. So if I give you a linear program, it might be in minimization form or in maximization form. You can create a new linear program by playing this game. So for minimization problems, you try to create lower bounds and you try to maximize the lower bound. Or for maximization problems, you try to create upper bounds and you try to minimize the upper bound. Okay. So what we did yesterday was we started with a problem, and there are many ways. Let me say one way. So you could have set up a problem of the following type: minimize C transpose X, subject to, let's say, AX equal to B, X non-negative. And from this, we derived this problem called the dual problem, which was to maximize P transpose B subject to P transpose A less than equal to C transpose. So we derived this yesterday. And the way I did this was I created a lower bound on this problem by relaxing these equality constraints and then tried to maximize that lower bound. And that gave me this particular problem. Okay. And so in this problem, there were n variables and there were m equality constraints. And there were, of course, n non-negativity constraints, while in this problem there are m variables and n inequality constraints. Okay, so we derived this yesterday, and I gave you, and you can do this for every LP. Okay, if I for example, if I was to change this to, let's say, ax greater than equal to b, x non-negative. Suppose this was my LP, then this dual will change. Okay, this will become PA transpose because x is non-negative. This will be less than equal to, and because this is greater than equal to sign, it turns out that P will have to be non-negative. So depending on what type of constraints you have here, the formulations will change a bit. Okay. And instead of deriving this every time step by step, you can do this for every LP of any form. You can do it. I gave you a table. The table tells you how to go from one form to another form. So when you have a minimization problem, and if you have a maximization problem for primal and dual, okay, if these constraints were greater than equal to constraints in the primal for a minimization problem, my dual variables will be non-negative, like in this form. If it was less than equal to, it should be less than equal to here. And if it is equality, my dual variable should be free. Okay. So so for example, here it's greater than equal to, the dual variables are non-negative. Okay. So remember they go in this form. Okay. Uh, the every primal constraint sort of corresponds to a dual variable, and every dual constraint corresponds to a primal variable. Okay, so this is where the so similarly, if I give you for the dual, if my constraints are, let's say, P transpose AJ less than equal to CJ, then my this primal variables have to be non-negative for a maximization problem, less than equal to, so it's greater than equal to 0. Okay, if it was uh, greater than equal to for a maximization problem, the corresponding dual variables will be less than equal to, and if it was equal, these will be free variables. Okay. So I showed you this table yesterday, and this table you should get comfortable with, because this will tell you anytime, depending on any primal form, how to convert, taking up a linear program, how do you write the dual? Okay. If I give you in a minimization form, you can go in this direction. If I give you a maximization form, you can go in this direction. Okay. So hopefully you're comfortable deriving the primal and writing the primal and dual. You can derive it from first principles, but every time you write a dual, you don't have to go back to deriving from first principles. Okay, you can use a table to derive to just write it down. Okay, but I did want to show you. We saw yesterday a couple of examples where we did it explicitly from first principles, so that you do understand the rationale behind it, what it is trying to do. Okay. Now, what was the most important implication of this? We basically saw two critical results which relate the primal and the dual. Okay. So first was yesterday we saw this concept of weak duality. Okay. So again, this is a recap from yesterday. What does this say? You take any solution to this problem and take any solution to this problem, and you compare the objective function at that point and the objective function at that point for the minimization problem. So C transpose X will be, for a minimization problem, the objective function coming from the minimization problem will be greater than equal to the objective function coming from the maximization problem for every primal feasible X and for every dual feasible P. So you take any primal feasible solution, take any dual feasible solution, compute the two objective function values for the if the primal is a minimization problem, the objective function from that will be greater than equal to that from the dual problem, the maximization problem. This is weak duality. Okay. This has nothing to do with optimality, it has to do with feasibility. So you take feasible solutions. Of course, this will imply a natural implication of this is the minimum of this is greater than the maximum of this. So it tells you that the minimization problem, the smallest value, will be bounded from below by the maximization of the dual problem. Okay. And we saw already this has a couple of implications. For example, if the primal is unbounded, so the primal goes off to minus infinity, because the dual bound has to be below, the dual also has to be minus infinity. It's a maximization problem, which means that this has to be infeasible, the dual problem. So we saw this yesterday, as an implication of duality. Another implication is if the two objective functions match, they have to be optimal. Okay. So the second theorem, the second theorem, which is strong duality, says that if the primal is feasible, the dual will also be, if the primal has a optimal solution, the dual will also have an optimum solution, and they too will match. So at optimality, the two solutions will match for an LP. Okay. As long as the primal has an optimal solution. Okay. Because remember, the primal might be unbounded, it might be infeasible, and so on. Okay. So this was strong duality. Okay. And so today we will continue with this discussion, and I will try to show you a few more implications from duality theory. Okay. So this was a recap from yesterday. Was there any question from yesterday's class? Any concept here which is unclear at this point? Again, extremely critical theorems, extremely important. Okay. So the first implication of strong duality is the following. Okay. So you can actually, so if you take a primal problem and if you take a dual problem and we think about what happens in an LP, we can either have a finite optimal value. The LP could be unbounded. That means it has got an unbounded optimal value, or it could be infeasible. These are essentially the three possibilities in LPs. We saw an LP can either be unbounded, it can be infeasible, or it will have a finite optimum value. Only one of these three things will happen for any LP. Okay. Similarly, for dual, you will have a finite optimal value, or it could be unbounded, or it could be infeasible. Okay. So there is total of 9 possibilities. Okay. Okay. So what does strong duality tell us? Strong duality says that if the primal has an optimal value, the dual also will have a finite optimum value. So only this can occur. Okay. So you cannot have one LP having a finite optimal value and the other LP being unbounded or infeasible. This cannot happen. Similarly, the dual cannot have a finite optimum value and the primal cannot be unbounded or infeasible. This cannot happen. Okay. This is strong duality. If one has a finite optimum value, the other also has to have it and they have to match. Okay. So these four possibilities cannot occur. Okay. As an implication of weak duality, we saw that if an LP is unbounded, if the primal is unbounded, the dual is infeasible. Similarly, if the primal is unbounded, the dual is infeasible. If the dual is unbounded, the primal is infeasible. This is from weak duality. This is strong duality. This is weak duality. Okay. That is one final case which can happen in LP. You can have an LP where both problems are infeasible. This can happen. Okay. It's a rare occurrence, but it can happen. Okay. So let me show you this example. So this last example, so both LPs might be, it's not going to be always the case. Both LPs might be infeasible. Okay. So it might be that one LP is infeasible and the other is unbounded, or it can be both are infeasible. Okay. So this is why yesterday I told you when you say a linear program is unbounded, it implies infeasibility, but the reverse need not be true. It doesn't mean that if an LP is infeasible, if a primal is infeasible, the dual has to be unbounded. The dual could be unbounded or infeasible. Okay. That's why the reverse implication I didn't say because it's not true yesterday. Okay. So what I mean, how do you see this? This possibility is we just have to construct an example where this occurs. Okay. And so here's one example. Suppose I try to minimize minus x1 minus x2 subject to x1 minus x2 greater than equal to 1, x1 minus x2 less than equal to 0, both x1 and x2 non-negative. Okay. So this is clearly infeasible. Okay. If this is x1 and this is x2, x1 non-negative, x2 non-negative, x1 minus x2 less than equal to 0. So this is like x1 equal to x2 is this line. To the origin. And so if it's on this side of the space. So this is x1 minus x2 less than equal to 0. And if you look at x1 minus x2 greater than equal to 1, it's a parallel line to this on this side. Okay. So clearly the intersection of these two half spaces there exists nothing in the space. So it's infeasible. So, I mean, you can make out from these two constraints, this is infeasible. Okay. So let's write the dual. So there's a dual variable for this constraint, a dual variable for this constraint. Okay. So if I assign P1 to this constraint and P2 here, this would be maximize 1 times P1 plus 0 times P2 subject to I check the coefficients for x1, P1 plus P2, compare this to -1, the coefficient here, and I need to figure out what the sign here is. And because if you look at the table, but because in a minimization problem, the variable is non-negative, in a maximization, the constraint will be less than equal. Likewise, if you take the x2 variable, the coefficients are -1, -1. So it's minus P1 minus P2. Compare it to -1. But because x2 is non-negative, this should go this way. And from these two inequality constraints, you can check that P1 should be non-negative and P2 should be non-positive for the dual formulation. So if I use a dual, you will get this form. Okay. And if you check this, you should be able to validate this constraint says P1 plus P2 is less than equal to minus 1. This says P1 plus P2 is greater than equal to 1. This cannot jointly occur. Okay. So if you try to plot this feasible region, also it will be unbound, it will be infeasible. If this is P1 and this is P2, P1 non-negative, P2 non-positive, P1 plus P2 less than equal to minus 1. Okay. That's going to be in this direction. And P1 plus P2 greater than equal to 1, that's going to be in this direction. Okay. Clearly, this is also infeasible. Okay. So this can occur in LPs. Okay. Both LPs can be infeasible. Okay. So out of the 9 possibilities, there are only 4 possibilities which can occur in LP. This is the most common case. This is comparatively rare. This can also occur. Okay. But these can never occur. These 5 cases. Okay. Any questions with this? This comes from strong duality. This comes from weak duality. The implication of weak duality, and for this we just have to create a counter example or an example where this can occur. Okay, so this is important because this tells you what possibilities exist between the primal and dual for LP. So this table is very important also. Okay. Okay. Any questions with this formulation or with the condition here, with the theory here? No? Okay. Good. Let's continue then. Okay. So what we'll do is we will look at a few more so we look at one more condition, one more property that comes out of strong duality, which is very useful, which is what is called complementary slackness. Okay. Again, we are trying to understand strong duality in many ways. Okay. Each of these ways is important and useful. So complementary slackness tells us something about how the primal and the dual uh, the primal constraints and the dual variables, the dual constraints and the primal variables, it tells you something about what have to, when they're together, what should happen at optimality. Okay, so here's the theorem. Let X be primal optimum. Sorry, let X be primal feasible and P be dual feasible. Okay. Then X is primal optimum and P is dual optimum if and only if. Okay. So this is an if and only if condition. If and only if the following conditions are the following conditions hold. AI transpose X minus BI times Pi is equal to 0 for all I. Cj minus P transpose Aj times Xj is equal to 0 for all j. Okay. So it is saying that every dual variable corresponds to a primal constraint. You look at the slack in the constraint and compare it and take the dual variable. One of these two has to be 0 at optimality. Similarly, one of the primal variable or the dual slack or the dual the whatever the difference between the left hand side and the right hand side in the dual constraint, at least one of this has to be 0 at optimality. Okay, so how do I get these? Essentially, if you look at the table, it says either this has to become equality or this has to be 0. At least one of this has to happen at optimality. Okay, both might occur, but definitely one has to happen. Okay. So that is complementary slackness. Okay. So it's another way to write the strong duality theory condition, and we will do that. Okay. This is quite useful sometimes in identifying from a primal optimum solution to a dual optimum solution, or vice versa. This condition is quite useful to sometimes go back and forth. Okay, and I will show you an example later. Okay, but let me first check that the theorem is clear. Statement is clear. Okay. Okay. So again, we're going to prove this. Again, the proof is actually not. It's similar to what we did earlier. We are going to look at. I'm going to just define. I'm going to look at how these terms behave. So we're going to create this duality gap between the objective functions. So you got this is the objective from the primal. That's the objective from the dual. I'm just going to write this in the following way. So all I'm doing here is I'm adding and subtracting the same term. Okay. And why am I doing this? Because I want to pick up this type of C minus P transpose AJ that's going to come from here, and the AI transpose X minus BI is going to come from here. So I'm just adding and subtracting the same thing. Okay. Now, if I write this if I go from this vector matrix products or vector vector products to the explicit forms, here I would have summation J. This is the first term, and this is the second term. Okay. So this is why sometimes going between the you have to start getting comfortable between going from the matrix forms and the column form, the column representations and the row representations. Okay. So just to remind you, hopefully this is clear. But you look at A. A can be either written as a set of rows. Let's say the M rows, or so each one is a row, or you can write it as columns. Okay. So you should start getting comfortable going between matrix row and vector column forms and row forms. So here I'm using the column form. Here I'm using the row form. Okay, it's the same matrix. Okay, is that clear? What are we doing here? This is a column A1 up to AN. So for example, when I'm looking at this P transpose AX, right? What is this? I'm thinking of this as P transpose A is simply, so what I'm doing is I'm writing P transpose A as summation. So this entire thing, P transpose AX, I'm writing this as summation J, P transpose AJ XJ. Or basically AX is the same as taking the column vector, multiplying it with the corresponding X. What I'm doing here is when I'm writing P transpose AX in the second term, I'm writing this as what I'm you can summation I PI AI transpose X. Okay. Is that clear, or is it not clear? Are you guys comfortable with these things? Row vector form. I mean, you've got to be comfortable. I mean, one of the things with these things is you need to be comfortable going from row forms, using either row representations or column representations. Okay. But it's the same matrix A. I'm just writing it in two different forms here. Uh, Anything here which is unclear? I can spend a bit more time. It's fine. Yeah. Yeah. Yeah, you mean in this part or here pi is the ith component, so it's a scalar. Okay, so what I'm doing here is when I'm writing p transpose ax, think about what I'm doing is think about what p is. P is basically that is p1 up to like p m. Okay, okay, and if you look at ax, okay, it's just a1 transpose x. So I'm doing this, writing this as summation I pi ai transpose times x. Okay, okay. So we're just writing this. I mean, why am I doing this? Because if you think about the way I've written this in this representation, AI is like AI transpose is like the row vector of the AI matrix of the A matrix. AJ is the column, jth column of the A matrix. The same matrix A shows up in both parts, right? The same matrix A is there on both sides, right? But yeah, I'm writing this in row vector form, and yeah, I'm writing this in column vector form. Okay. I mean, you can also write this as A transpose. I mean, what is this constraint? This constraint is the same thing as A transpose P less than equal to C if you want. I'm just taking transpose 2 out. Okay. Okay. Is that clear? Okay. Fine. Okay. So what do we know about this? So let me okay. So this is extra. So let me just put this here. But let's go from this equality. What do I know about this equality? Okay. So each of this. Okay. So if you look at the table. Okay. If this is non-negative, this is non-negative. I mean, this is what we did also in the strong duality proof. But basically, I'm sorry, in the weak duality proof. But basically, these two are the same sign. So if this is non-negative, if this is greater than equal to, this is greater than equal to 0. Okay. So essentially, from the this this term for the feasible solution, this will always be greater than equal to 0 because AI transpose X minus BI and PI, this term will always be greater than equal to 0 for all I, and Cj minus P transpose Aj times Xj is always greater than equal to 0 for all j. Okay, how do I get this? I get this from this table. Cj minus P transpose Aj is non-negative, Xj is non-negative. It's negative, less than equal to 0, it's less than equal to 0. So product will be non-negative. And if it is equality, it becomes anyway 0. Okay. So this term that we are creating, this duality, I mean, actually, this is nothing but just weak duality written again. Okay. I'm just writing, this is the duality gap, primal and dual values. Okay. I'm just saying that the primal objective is greater than equal to the dual objective. Right. So I'm just restating weak duality again, except now I will look at term by term what happens. Okay. Okay. So what happens? So let me just take this. Okay. So actually, let's go to the next page. So okay. So what do I want to argue? I want to argue that optimality for primal and dual means that each of these terms has to be equal to 0. Okay. So let's start with one direction. So suppose each of these, so if let's say each of these terms are equal to 0. Okay. If each of these terms is equal to 0, if this term is equal to 0, if this term is equal to 0 and this term is equal to 0, It means that C transpose X and P transpose B are the same. Okay. So if AI transpose X minus BI times PI is 0 for all I, and CJ minus P transpose AJ times XJ is 0 for all J, then what does it mean? Then C transpose X minus P transpose B is equal to 0 from the previous, the way I wrote the duality gap. Okay. This then, so therefore, X is primal optimum and P is dual optimum. Why? From the implication of weak duality, right? What did weak duality tell us? If one of the implications of weak duality was, if I give you a primal feasible and dual feasible solution where the objective functions are the same, they have to be optimum. This was the implication from weak duality. Implication or from the corollary of weak duality. Okay. The moment you create for me a primal and dual feasible solution which have the same optimal value, same objective value, they both have to be optimum. Okay. So this side is straightforward. The other side also is straightforward. So why is the other direction true? So suppose, so if X is primal optimal and P is dual optimum, then from strong duality, what do we know? C transpose X minus P transpose B has to be 0. Because strong duality says that the optimal values have to be the same. If they are the same, if these two terms are the same, so this thing becomes equal to 0, and each term here is greater than equal to 0. So if I give you a sum of terms and a sum of terms which equal to 0, where each term here is non-negative and each term here is non-negative, the only way this can occur is if each of these terms itself is 0. I mean, you cannot have any positive value here. If you're adding up non-negative numbers and making them equal to 0, every number has to be 0. Okay. So therefore, it has to be the case that AI transpose X minus, so each term must be 0. Therefore, AI transpose X minus BI times PI is 0 for all I, and likewise for the dual constraints and primal variables. Okay. So again, it's just a restating in some ways of strong duality and weak duality, but done through this what is called complementary slackness conditions. So these conditions again will show up a lot. They are called complementary slackness conditions. You have some conditions like this even for yeah, I mean, you will sometimes get such condition. You will get such conditions also for convex optimization problems. Okay, more broadly. Okay. Okay. So let's try to interpret these conditions. But are the conditions clear? It's a statement about optimality. Okay. So let me give you some intuition. So note. So what is this condition trying to say? Okay. So let's take an optimization problem of the following type. Let's say this is my feasible region. Okay. So there are different constraints. Let's say A1 is a vector pointing in this direction. Let's say A2 is pointing in this direction. Maybe A3 is pointing in this direction. And A4 is pointing in this direction. Okay. So the feasible region is essentially all this space. Okay. All this space is the feasible region. Okay. So let's say my primal problem is to minimize C transpose X subject to, let's say, AI transpose X greater than equal to BI for I going from 1 up to 4. Okay, let's just say this is the problem. Okay. And let's say my vector C is increasing in this direction. Okay, so C is increasing in this direction. So my optimal solution going in this direction has to be in this direction down. So it has to be this. So this should be X star. Okay. Where at C, this X star is pointing in this direction. Right. So this should be X star. So X star is primal optimum. Is that clear? What we are doing there? This is like A1 transpose X equal to B1. Let's say that's the hyperplane, the half space is in this direction. Okay. So that's my feasible region. Objective is increasing as I go in this direction. So in this direction, the minimum is here. Okay. So what is the dual problem? The dual problem says what? The dual is, so let me write the dual. The dual will be maximize I from 1 up to 4, PI, BI, okay, subject to, okay, I can write this P transpose A less than equal to, so PI, so because these constraints are non-negative here, the constraints are greater than equal to in a minimization problem, all the dual variables have to be greater than equal to 0. Okay. And I can write the constraint. So it's like P1 times A1, compare it to C1, X is free. So what you will have is, so C will be equal. So you will take some summation Pi AI has to be equal to C. This is equality because X is free. Okay, so this is a dual problem. You got 4 inequality constraints, so you'll have 4 dual variables. They have to be non-negative. Okay, is it clear? Okay, so let's look at what complementary slackness tells me. So what is A1? A1 is pointing in this direction. Okay. So if I take this A1 vector, sorry, I should not move this. Okay. So let's look at A1. So A1 is perpendicular to this hyperplane. Okay. So A1 is in this direction. This is the A1 vector. Okay. What is A2? A2 is in this direction. Okay. What is this condition telling? What is complementary slackness telling me? It tells me that AI transpose X star minus BI times PI, the optimal dual variable, has to be equal to 0 for every I. Okay. This is one set of complementary slackness conditions. The second one is these values are the summation PI AI is equal to C and PI is non-negative. Look at this point X star. At the point X star, what happens? At the point X star, sorry, at the point X star, A1 transpose X star is equal to B1. It's on this hyperplane. A2 transpose X star is equal to B2. But A3 transpose X star is strictly greater than B3. It's not, this point is far away from this hyperplane. So it means that because this number will be strictly positive for the A3 constraint, P3 has to be 0. Okay. So from complementary slackness, P3 star should be 0 and P4 star has to be equal to also 0. Right. This point X star does not lie on these two lines. So from this condition, this number will be strictly positive, which means this value, the dual variable for these two constraints have to be 0. Why is this the case? It means that these constraints are not playing a role in the optimal in they are far away from the optimal solution. So even if I was to change these constraints a little bit, actually, they don't affect my optimal solution. Even if I rotate these constraints a little bit, they won't change my optimal solution. The constraints are not providing any useful value on the optimal solution. Okay. If P3 and P4 are zero in this equality constraint, it means that P1 star A1 plus P2 star A2 is equal to C, where P1 star and P2 star are potentially non-negative. That means you can write C as a conic combination of A1 and A2. Look at the figure. P lies in the cone created by A1 and A2. It lies inside this. So it's a non-negative combination of these two vectors. Okay. So that's very, very nice geometric interpretation of complementary slackness. Okay. You can write C, even if I was to take this constraint and move A4 a little bit, even if I was to tilt this constraint, okay, even if I deleted this constraint and I simply shifted this a little bit, actually it doesn't change the optimal solution. It will still be this point. Okay. Because this A4 doesn't play a role. The dual variable corresponding to this constraint is not playing a role in the optimal solution. Okay. There is a slack. Okay. Okay. Any questions with that? Again, I found this, complementary slackness will always be a very important condition. It's a very useful condition because you can always, typically, you can use it to go from a primal optimum solution to a dual optimum solution. Okay. Not always, but many times. Okay. And so I'll tell you so let me make a comment here. Any question with this figure? Was it clear what I was trying to convey or? Okay. So let's make a note here. Okay. So how do we use complementary slackness? So it turns out that if we have a non-degenerate, so if we have a non-degenerate optimal basic feasible solution, let's say for a standard form LP, okay, so there's an assumption here of non-degeneracy, then we can use complementary slackness to find actually a unique dual optimum. Okay, so it actually turns out that a non-degenerate primal optimum solution will give you a dual optimum which is unique. Okay, so and I'll come back to this, but basically degeneracy in the primal corresponds to multiple optimum in the dual, and degeneracy in the dual is multiple optimum in the primal. Okay, but let's think about why non-degeneracy in the if you have a non-degenerate optimal BFS, I claim you can find a unique dual optimum. Why is this the case? Think about standard form LP. C transpose X, AX equal to B, X non-negative. At optimality, my basic variables should be B inverse B. Because I'm assuming it is non-degenerate, these values have to be strictly positive. Degeneracy says that some basic variables will go to zero for a standard form LP. Non-degenerate solutions, Xn star, will be equal to zero. Okay. Okay. Now, what is the complementary slackness conditions telling me? AX, I've got this condition saying P transpose AJ minus CJ times XJ bar is equal to zero from complementary slackness. Complementary slackness. Right? This is my condition, right? This thing has to go to zero. For every basic variable, for all the basic variables, these numbers are going to be positive. which means that this has to go to 0. So for basic variables, if you take the columns corresponding to the basic variables, you will get P transpose B minus the costs corresponding to my basic variables. This entire vector should be equal to 0. Okay, because why is this? Because xb star is strictly positive. So for every basic variable, I get a positive value here, which means this has to be equal to 0. So this is column by column. So I'm just writing this now for the entire basis matrix. Okay. But if this is true, then what is P transpose? It's quite clear. P transpose should be, you just invert, right? P transpose B is equal to CB transpose, but B is invertible. So P transpose is simply CB transpose B inverse. So P is uniquely determined, the optimal dual solution P star or P. Okay. And you can also see why it's a unique dual optimum. There's no other P you can find. Okay. Complementary slackness says that this has to become 0 and B is invertible. So you can find only one P, which is going to solve this problem. Okay. So this is another maybe important thing. Degeneracy in primal is actually going to be multiple optimum in dual or non-degeneracy in the primal. So at an optimal solution, if I give you if I find a non-degenerate primal optimum solution, I'm actually going to find a unique dual optimum. Okay. Okay, so let's do maybe an example and then we can take a break. Any questions with this argument? So let's just do one example. So just a quick example just to illustrate the use of complementary slackness. Okay. Again, I'll go back to the same example that we did in the simplex method. So when I showed you the simplex method, I solved this problem. Okay. We solved this using the simplex method. Okay. So let's just look at this one problem just to get a sense of how you use complementary slackness. So this is a standard form LP. This is the primal problem. We solve this using the simplex method. And suppose I solve this problem and I told you that the optimal solution was x1 is 1 and x2 is 2. In fact, this is what we found using the simplex algorithm in week 3, in last week. Okay. Of course, if I know x1 and x2, I know what the slack variables are. So S1 is 2 and S2 and S3 are 0 in this problem. Okay. So suppose I give you the primal optimum solution. I want to find the dual optimum. Okay. What is the dual problem? I maximize P1 plus 4P2 plus 2P3 subject to P1 plus 2P2 compared to minus 3. This should be less than equal to minus P1 plus P2 plus P3 less than equal to minus 2. P1 should be less than equal to 0. P2 should be less than equal to 0 and P3 should be less than equal to 0. Okay. So I should not have made any mistake, but this is a dual formulation. Okay. So this is actually a non-degenerate optimal basic feasible solution. Wow. How do I know this? I claim this is a non-degenerate optimal BFS. Why? For the primal. How many basic variables do you expect? Should you have? 3. There are 3 equality constraints. 3 basic variables, all 3 are positive. Strictly positive. So this is a non-degenerate primal optimal basic feasible solution. Let's find the dual optimum using complementary slackness. What does dual optimality say? Sorry, what does complementary slackness say? You take this corresponds to the x1 constraint. So P1 star plus 2P2 star take this aside, plus 3 times x1 star should be equal to 0. But x1 star is positive. So because x1 star is positive, this implies p1 star plus 2p2 star plus 3 should be equal to 0. Okay. This has to go to, this has to be tight at optimality. Okay. Likewise, minus p1 star plus p2 star plus p3 star plus 2 times x2 star should be equal to 0, which means that I've got minus p, because this is strictly positive, minus p1 star plus p2 star plus p3 star should be equal to 0. So I'm getting two conditions which I've got three dual variables, okay? So I found two conditions so far, two equality conditions. S1 corresponds to this constraint. S1 corresponds to this constraint. So S1 star times, so P1 star minus 0 times S1 star should be equal to 0. But S1 star is positive, which means P1 star has to be 0 because this is strictly positive. The moment I find P1 star equal to 0, I got essentially three equalities. I should be able to solve for three variables. P1 is 0, solve for P2 and P3. Okay. So if you solve this, solve for P2 star and P3 star. Okay. What is this? So if P1 is 0, P2 star is clearly minus 3 by 2. Minus 3 by 2. And if P2 star is minus 3 by 2, P3 star should be, I'm sorry, this should be a plus 2. Huh? You didn't tell me. This should be plus 2. Plus 2 equal to 0. There's a plus 2 here. So if this is a minus 3 by 2 plus a 2, that's a half. Half plus some number is equal to 0. So this should be minus half. Okay. Check that it satisfies all the other dual constraints. P2 should be less than equal to 0. True. P3 should be less than equal to 0. True. I found P1 star, P2 star, P3 star. This is dual feasible and dual optimal. Okay. So P1 star should be equal to 0. P2 star should be minus 3 by 2. And P3 star should be minus half. You can check strong duality. What is the objective function at 1, 2? Minus 3, minus 4, minus 7. If P3 is minus 3 by 2, that's a minus 6. 2 times minus half, minus 1, minus 7. Objective functions match. Objectives match at value of minus 7. Both primal and dual give you a value of minus 7. So you solve the dual by just taking the primal optimum solution and using complementary sloughness. Okay. Okay. Again, it's very useful. It's useful algorithmically because you can go from one set of optimal solution to the other one. Okay. Okay, any questions with the coverage so far? So we covered complementary slackness, strong duality, and weak duality. Of course, we have done. And what are the relationship between the primal and dual? Okay, the relationship between these two problems is extremely critical. Okay, and you should get comfortable working with either formulation over time. Okay, so we'll take a break now. When I come back, I will discuss a little bit more about duality, a few more points which I want to say, a couple of other results which are useful. Uh, okay, so let's take a break. We'll start in about 7 minutes. Okay. Let's continue. Okay. So what I'll do is in the next maybe 45 minutes or so, I want to complete some of the other points regarding duality. So one thing we have not spoken about is interpretation. Okay. So we have not uh, discussed what these p variables mean actually. Okay. So what is, and it depends on the problem context. Okay. But essentially, you can think about the optimal dual variables. Okay. Uh, as a sort of a price. Okay. Uh, okay. So for any resource, how valuable it is. So the dual variables tell you this. Okay. And depending, and you will find this actually. So one of the things that researchers do is depending on the class of optimization problems they're studying, they will try to interpret the dual in that context. What does the dual problem actually mean in that context? Okay, so depending on, I mean, you might have a LP coming up in a finance problem, the dual variables will mean something there. You might have it showing up in this sort of moment problem, which I showed you. I think one of the homework questions I gave you this thing called a moment problem, where you have to find a distribution. The dual variables there actually correspond to some non-negative polynomials. So depending on the problem context, dual variables mean different things. And so one thing that researchers will do when they're studying LPs in some contexts is interpreting the dual. Okay, let's just take one example here to illustrate this. Okay, just to give you a sense, because so let's take maybe the diet problem as an example. Okay, so remember what the diet problem is. I showed this to you in week one. It's a problem where you're trying to, so you have uh, you're forming a diet for yourself. So you're consuming certain items of food. Okay, maybe a packet of, I don't know, biscuits, maybe some rice, maybe wheat. Okay, maybe noodles and so on. Each of this gives you some amount of protein, vitamins, carbohydrates, minerals, fat, whatever. Okay, so you are trying to create a diet at minimum cost. Okay, so that the the total amount of nutrients you get from the diet at least matches your daily requirements for each nutrient, and you're identifying how much of each item of food to eat. Okay, so again, just to remind you, in this problem, CJ, let's say, is $1 per unit of food J. Okay, so food J could be maybe a packet of noodles. Okay, or maybe a carton of milk. Okay, so CJ is the cost for that. You want to minimize the cost of your diet. XJ is the unit units of food J you consume. Okay. What is AJ? The jth column of A matrix is basically the amount of nutrients per unit of food J. Okay. So a packet of noodles will have a certain amount of protein, certain amount of vitamins, and so on and so forth. And likewise, B is the minimum requirement of these nutrients for your diet. Okay. Okay. So you should remember this problem from week one. Okay. Okay. So that's a LP. It's a linear programming problem, which was one of the earliest LPs set up for the one of the first applications of LPs. Okay. You can do this for diet for yourself, but imagine you're running a farm, you have cattle, you have to plan the cattle diet basically. Okay. Okay. Now let's write down the dual for this problem. So dual means there'll be a dual variable for each constraint, and it's a minimization problem. So this will be a maximization problem. The right hand side will go to objective. The objective will come to right hand side. The P transpose A will be less than equal to C transpose. This is of this form because X is non-negative, and the P's here have to be non-negative variables. Okay. So let's try to interpret. So we know now that when we solve the primal, we are also solving the dual, and we can go from the primal optimum solution to the dual optimum solution, and the objective values match and so on. Okay. So let's think about how to interpret the dual. Okay. This dual variable P is of the same dimension as the number of nutrients you have that you're worried about in your diet. Okay. So you can interpret Pj, or let's call this Pi actually. Pi is the price of nutrient I. Okay. Of 1 unit of nutrient I. Okay. You may not be able to go and ask for one unit of protein. Okay. Or 1 unit of, I don't know, 1 calorie. Okay. But suppose you could buy in this nutrient market directly. What would the price of the nutrient be? How should these nutrients be priced? They should be priced. Okay, so how do you interpret the constraints? So you maximize. This is the amount of I mean, you can think about B as the amount of nutrients you require, right? So if I tell you this is the price of unit uh, for every unit of a nutrient, if that is the price, and you want to consume BI units of nutrient I, BI times PI is the price you're going to pay for that. And if you do this across all the nutrients, so maximize the total revenue from the nutrients, from selling nutrients directly. Okay. And the question is, why would somebody buy only instead of consuming? I mean, of course, this is a hypothetical situation. Okay. Instead of consuming noodles, if I told you I can give you some amount of protein, some amount of carbohydrate, some amount of vitamins, and so on and so forth, and you are willing to consume this, why would you do this? No, you would do this directly when? So your constraints tell you what you would. The pricing should be such that after you consume these nutrients directly, it should be cheaper than buying a packet of noodles. So you will only trade in this nutrient market, or you'll buy in this nutrient market if it is cheaper, because I can get the same amount of nutrients by consuming 1 unit of the let's say one packet of noodles. Okay, so I will only maximize the revenue from selling nutrients directly, where the prices should be chosen. So prices have to be non-negative clearly, where prices are chosen. So this constraint tells you what? So that it is attractive for the consumer, attractive for the consumer to buy directly from the nutrient market. Okay. Again, what does this mean? Why will the consumer be willing to buy in this market? Only if it is cheaper. The amount of one packet of noodles gives me some amount of, let's say, proteins and some amount of vitamins. If I can get these amounts, the price I pay is that much, P, times the amount I have in one packet. If that price is lesser than buying directly a packet of noodles, so only then I will trade in this market, or I'll consume in this market. Otherwise, I'll not buy in this market. There's no value for me. What does duality tell me? It tells me that in this food market, which is the market we don't, of course, consume these things directly. This food market or this nutrient market, these two things are essentially, duality says that they are essentially equivalent ways of. So duality simply provides alternative ways, alternative ways of accounting for the costs. Okay. Okay. It tells you, I mean, this is the market, of course, we trade in. You're worried about your diet. But suppose I could sell directly nutrients to you, then my nutrients should be priced so that it is cheaper to buy in this nutrient market than to directly consume the products that you're buying. And I will do this to maximize my revenue. Okay. So if there was a hypothetical person selling these nutrients, this is what he or she would do. And these two markets are the same, essentially. Okay. So this P, in some ways, what P tells you is how important a particular nutrient is. What is the value of it? Okay. So it's a price basically. Okay. You will also see things like, you will see sometimes terms like dual prices, Lagrangian multipliers, dual costs. The same term comes up in different ways. Okay. It's basically a price of a constraint or a resource. Okay. If you think about B as a resource, how valuable is that resource, a unit of the resource? Okay. Okay. Again, you can interpret duality depending on the problem context in different ways. Next week, when we do a bit of sensitivity analysis, I will again show you how the dual variables will be useful there. Okay. Okay. Any questions with this interpretation? Okay. So I want to show you two more applications of duality. And I just want to talk about, so what I want to do is just to complete up duality, I will show you one application of duality in this thing called Farkas lemma, something about how to represent polyhedron. And then I want to touch on the dual simplex method. We won't cover the dual simplex method. I'll just tell you the idea of it. Okay. Okay. So let's talk about another now. So these are applications of duality. Okay. So this is called the Farkas lemma. It's also called the theorem of alternatives. Okay. It's going to be again an application of duality theory. Okay. So let me tell you what the theorem is. Suppose I give you a matrix A of size m by n and B in Rm, then Rm, then the Farkas lemma says, then exactly one of the following two alternatives hold. Okay. So what is the theorem? It says either there exists an x in Rn plus such that Ax is equal to B. Okay. Just to remind you, this means that x is in dimension n and it is a non-negative vector. Okay. Or there exists a P in Rm such that P transpose A is non-negative and P transpose B is strictly negative. Okay. So you can see already by just looking at the statements, this looks something like duality. That is some x. No, this looks like the feasible region of a standard form LP. And this is something to do with dual variables of the dimension of B and something about the signs of these constraints. Okay. So this is going to be, so what is this theorem telling you? And I will show you how you can use this lemma. Okay. So the lemma says, if I give you any matrix A of size m by n and B of matrix size m, a vector, either you can find an x which is non-negative so that Ax is equal to B, or you can find a P in Rm so that P transpose A is non-negative and P transpose B is strictly negative. Only one of these two can hold. In fact, exactly one can only hold. So you cannot have both happening together. That's a lemma. Okay. So let's try to prove this, interpret it, and I'll show you an application of this. Okay. Again, it's going to be an application of duality. Okay. Okay. So we need to prove that only one of these two holds. So we're going to again do this in two steps. So step one, suppose one holds. Okay. If one holds, I have to show that two cannot hold. Okay. So suppose one holds, what does it mean? There exists x non-negative such that Ax is equal to B. I can find some such x. Okay. Let's multiply both sides by P. Multiplying by P, okay, or P transpose, we get what? P transpose AX is equal to P transpose B. Okay. And now I think about P transpose A times X. Okay. X is non-negative. Okay. X is non-negative. Suppose P transpose A was non-negative. P transpose B has to be non-negative. It cannot be negative. So if P transpose A is non-negative, because X is non-negative, P transpose B has to be non-negative. So it cannot be the case that P transpose B is negative. Okay. Therefore, 2 cannot hold. You cannot find me a P so that one side is negative and this is strictly negative and this side is non-negative. This cannot hold. Okay. So this condition cannot hold. Okay. Is that clear? This is straightforward. Okay. We're not using duality here really, but it's just straightforward. Any questions there? For any P, you cannot have this number to be non-negative and this number to be negative. This cannot happen. So I can never find such a P. Okay. So now we need to show the other direction. Okay. Or the other way is to show that if one does not hold, so suppose one holds, two does not hold. If one does not hold, I will show two holds. Okay. So suppose now one does not hold. Okay. Suppose one does not hold. Okay. And that means that you cannot find X non-negative so that AX is equal to B. Okay. And so a standard way to tackle these type of theorem of alternatives is to set up a primal dual LP and to use duality. Okay. So we're going to set up a primal dual LP of the following type. If one does not hold, it means that AX equal to B, X non-negative is infeasible. Okay. So if you think about AX equal to B, X non-negative, so consider the LP AX equal to B, X non-negative. I'm going to just, there is no objective. So I'm just going to make this maximum 0 times X. Okay. So there's no LP given to me. I'm just setting up an LP. Okay. This LP is infeasible. Okay. So observe that if one does not hold, primal is infeasible. Okay. Let's write the dual. What is the dual? Minimize P transpose B, compare P transpose A to 0 transpose. This should be greater than equal to because, I'm sorry, actually this should be, yeah, this should be greater than equal to 0 because X is non-negative and P should be free. Okay. That's a dual. Okay. So now let's remember what we learned earlier. If the primal is infeasible, what are the possibilities? The dual can be either unbounded or infeasible. Right? The two possibilities. If a linear program is infeasible, the other LP, the dual, will either be unbounded or infeasible. Only one of two possibilities. Okay. But this dual LP is not infeasible. Okay. So dual, therefore, dual is either infeasible or unbounded. This is what we got from strong duality and weak duality earlier. Okay. But clearly, this is not infeasible. Why is this not infeasible? Simply put, P equal to 0. P equal to 0 is a feasible solution for this problem. Okay. So dual has to be unbounded. Okay. What does it mean for this LP to be unbounded? You can find me a P. What does this mean if it's unbounded? I can make the objective go off to minus infinity. Okay. Think about what this P is. This implies there exists a P such that P transpose A is non-negative, and P transpose B has to be strictly negative. Why? Because this is what unboundedness means. I can simply scale, because I can take P and simply scale this to be as lambda times P, where lambda is some non-negative number. I keep scaling. I take a vector P and I keep multiplying every component of P by lambda. This will still be feasible because P transpose A is non-negative. So if I multiply by lambda, it will still say non-negative. And lambda times P transpose B will keep on pushing it down. So as I push lambda up, so push lambda up to infinity, you will get infeasibility. Okay. So as long as you can find a P which is where this is feasible and the objective function is decreasing in that direction, you're done. But this is exactly what this means: two holds, right? So one does not hold, but then two holds. So we proved the second case. So one can either hold or not hold. If one holds, two does not hold. If one does not hold, two holds. There are only two possibilities for one, right? It either is there or not there. It's either feasible or not feasible. Okay. So again, the trick here is to set up the right primal dual formulations. Okay. And this is a trick that gets used a lot for these theorem of alternatives. You take up a you set up a LP, you take duality, and then use this unboundedness infeasibility idea to try to prove the result. Okay. Okay. And there are many versions of the Farkas lemma. There are variants of this problem. I think in the homework, I've asked you to try out some variant of this. Okay. But this type of argument where you use a primal, you create an LP, you take its duality, and then you use the relationship between the primal and dual to prove something is a very useful idea. Okay. I'll show you an application of this result next, but is there any question about this? Actually, let's think about this geometrically first. But is the result clear, the proof clear? Any step of the proof that's unclear, or okay? Okay. Let's look at this geometrically. So suppose I give you vectors, let's say A1, let's say this is a vector A2. These are column vectors, okay, of the A matrix. Let's say A3 and so on. Okay. And let's say I tell you that uh, P transpose A is non-negative. Okay, so I'm looking at the case when two does not hold. Oh, I'm sorry, actually two holds. Okay, so suppose two holds. Okay, what does it mean? If P, so suppose two holds. So this second case, right? P transpose A is non-negative. It means P transpose A1 is non-negative. P transpose A2 is non-negative. P transpose A3 is non-negative. The dot product between P and the column vectors of A are non-negative. Okay, that means that P is forming an angle which is less than 90 degrees with each of these vectors. Okay, so maybe the P looks something like this. Okay, these angles are less than 90 degrees, right? This is uh, the angles here are less than 90 degrees. Okay, if I say P transpose B is less than 0, what does it mean? It means B forms an angle which is more than 90 degrees with P. Okay, so maybe B is going in this direction. Okay, so P transpose B is a larger angle. Okay, what does, so this is two holding, right? So P transpose A is non-negative for each column vector, and P transpose B is negative. So what does this mean? You cannot find me an X such that AX is equal to B. B does not lie in the conic combination of these vectors. Okay. Another way to say this is there's a separating hyperplane. Okay, and we'll come back to this idea later when we do the ellipsoid method. Sorry. This is a 90-degree angle with this vector. So if you look at this hyperplane, let's call this all z. This is a vector of, let's say, all z, where p transpose z is equal to 0. Okay. So all these form acute angles with p. This forms a greater 90-degree angle with p. Okay. So you can separate. So b lies on one side and the remaining a's lie on the other side, basically. So I can find a vector, separating, this is called a separating hyperplane. I can find a separating hyperplane which can separate each of these A vectors, column vectors, from the B vector, basically. Okay. Or B does not lie inside this set, basically. It does not lie in the conic combination or the conic hull, basically, of these vectors. Okay. Is that clear geometrically what's happening there? Okay. So let me show you one quick application of this. Am I going too fast or is it okay, the pace? Okay, okay, okay. So let me show you one application of this result quickly. So application of Farkas lemma to asset pricing. Okay, application of Farkas lemma. Okay. Again, I'm just going to give you a like a taster of how you can use this. You can spend a lot more time studying this, but I'll try to give you an idea of how you can use this for asset pricing. Okay. So if you do finance, you will spend a lot of time studying things like no arbitrage conditions, pricing of assets, and so on. It's also it's a form of using duality. So I'm going to just show you how you can use Farkas lemma in that. Okay. So this is now we are in the financial world. Okay. Okay. And we're going to keep things simple because the goal is to show you an application. So I just want to show you the application. So imagine we are uh, in a financial world where so there are basically m states of nature, okay, or m possibilities. Okay, so maybe the economy tomorrow will be good, or maybe the economy will be moderate, maybe the economy tomorrow will be bad. We don't know. Okay, there are n states of nature in the future. Okay, and there are n assets. Okay, so these are maybe things you invest in. Okay, okay, maybe stocks if you want. Okay, okay, you have a payoff that matrix. Let's call this R. Okay, this is a matrix of size. So you have got the ith column and the jth entry. This is called Rij. Okay, so I've got m rows, n columns. Okay, so what is Rij? The ith row and the jth column. Rij is the payoff of asset I, sorry, of asset J in state I. Okay. So what does this mean? If I buy 1 unit of asset, okay, let's say it's buying 1 unit of stock. Let's say General Motors. I buy a stock of General Motors. How much will it pay off if the state of nature was the ith state? Okay, maybe the economy is good. Maybe I'm going to get good payoff. Maybe the economy is poor. I'm going to get a bad payoff. Okay. So each of these assets has a payoff. Okay. Okay. Is that clear? That's a data. Okay. R. It's a matrix. It might be a very big matrix if you've got many states of nature. We are assuming at this point everything is discrete. So there are only m states. Okay. Okay. What can you do? You can invest. So X is a vector of size n. Investment in the assets. Okay. So X is in Rn. Okay. So you can invest in each asset. Okay. And technically, you might buy assets, but there's also in finance this idea of shorting, okay, where you can buy negative basically. Okay. So I don't want to get into that, but you're essentially investing in these assets. Okay. It can be positive or negative. Positive means you're buying, negative means you're shorting on these assets. Okay. Okay. What is the payoff? Okay. The payoff is a vector W, which is R times X. Every state of nature, so you take R, you multiply with X. What W tells me is if the state of the nature tomorrow was good, how much would my payoff be if I had bought this set of assets with uh, such a portfolio? If my state was bad, what would my payoff be? So this is a vector of dimension. So W here is in RM. Okay. Okay. And the last thing you require is to invest in these assets, you have to pay a price. Okay. So P is the price of investing in assets. Okay. So for example, if I buy a vector portfolio X, P transpose X is the cost I have to pay, right? The price I have to pay. So P transpose X is the price of the portfolio I form. Okay. Okay. So you are trying to invest in assets. That's a vector X. You're trying to maybe buy 100 stocks of General Motors, maybe 50 stocks of something else, and so on. You create this portfolio. For each of these units of stock, you have to pay a price. So P transpose X is the price of this portfolio you formed. You make this portfolio Y because you don't know what's going to happen in the future, but you're hoping that in the future you make payoffs. Okay. Okay. So what is the basic So, what is the one of the most basic conditions in finance? So, essentially, in finance, the prices of assets are based on one simple condition which they have to satisfy, what is called the no arbitrage condition. Okay. So, what is the no arbitrage condition? You cannot make money for free. Okay. Or the prices should be such that people cannot make money for free. Okay. If I'm going to tell you 100%, I'm going to give you, no, you have to pay. And how do you say that? Essentially, it says that if your payoffs are going to be non-negative for every state of the nature, then you have to pay a price for this. If I'm going to tell you with a certain guarantee that tomorrow you're going to make positive payoffs in tomorrow's state of nature, tomorrow whatever happens, then today you better pay a price for forming this portfolio. Okay. So this has to be true, and the prices have to be chosen so that this condition holds. If you get non-negative payoffs in the future for every state, you have to pay a price for forming this portfolio today, a non-negative price. Okay. So this is called a no arbitrage condition, which essentially says that any portfolio vector which has a non-negative payoff in every state of the nature in the future has to have a price to be formed today, a non-negative price. Okay. Okay. So basically, finance pricing is based on the no arbitrage condition. Okay. The prices you see in the markets. Okay. Okay. So what is the theorem from Farkas? The theorem says that no arbitrage, no arbitrage, no arbitrage is equivalent to saying that exists a, a price vector which is non-negative such that the prices you see in the market today have to be given by a combination, this non-negative combination of these payoffs. Okay. So this is what the theorem says from Farkas lemma. Okay. I'll try to interpret this condition in a bit, but let's first see why this is just an application of the Farkas lemma. Okay. What is Farkas lemma saying? No arbitrage. What is no arbitrage saying? You cannot find me an X in Rn. You cannot find me a portfolio so that Rx is non-negative and I don't have to pay money. I actually get money for forming the portfolio. Okay. If you give me money to form the portfolio today and I'm getting non-negative payoffs tomorrow, I will arbitrage you out of this, right? I'll make infinite amount of money. Because in the future, I'm guaranteed of payoffs or non-negative payoffs. And today I'm paying negative cost price, which means you're actually paying me to form the portfolio. Okay. Okay. But this is nothing but statement 2 of the it says that 2 does not hold basically. If you look at what this condition is, what is this condition? You cannot find me an x in Rn, so that Rx is non-negative and P transpose x is negative. Okay, it's simply saying that this condition does not hold, which means this condition has to hold. Okay, that's what our Farkas lemma says. So if you write that for this problem, so from Farkas lemma, okay, this says there exists a Q in Rm plus, so that remember P, the price vector is in dimension n. Okay, and this Q vector is in dimension m. So this should be P equal to R transpose Q. So R is of size m by n. So R transpose is n times n. Okay. Okay. So what is this actually telling me? Okay. It is telling me that there exists this. So what is this vector Q? For every state of, so instead of think about pricing for every state of nature. Okay, suppose I gave you a different market where for every state of nature which can happen in the future, there was a price. Okay, if I told you with certainty tomorrow this is going to be the state of nature, so there will exist some price for each state of nature, so that the prices you see today in the market for each portfolio essentially has to be obtained by, because for every state of nature you're getting a payoff. Okay, so this basically gives you a linear combination of those prices basically. Okay, so essentially you can think about, so we can interpret Q as a state price vector. Okay, basically what is this? Essentially an imaginary asset, if you want, an imaginary asset that pays one that pays one if a certain state of nature occurs and zero otherwise. If a certain state of nature occurs and zero otherwise. Okay. So if I told you with certainty what's going to happen tomorrow, okay. So suppose there was, so this is an imaginary market. This doesn't exist. Okay. But essentially, you can find such prices for every state of nature, so that the prices that you're seeing in the market today are given by that potential prices for the future states of nature in terms of the payoffs. Okay. Another way you can think about this is in finance, there's something called a risk neutral measure. That means the prices today have to be, they have to take the fact that for forming the portfolio today, for tomorrow's, because you're going to make money potentially in the future, the prices that you're seeing. So there's something called a risk neutral measure. So you can actually interpret this as something called a risk neutral measure. Okay. Again, this is not a class in finance, so I don't want to spend all the time discussing this, but you can there is a essentially there's a different pricing strategy for uh, uh, for these states of nature. Okay, and so what this Farkas lemma simply says is, for asset pricing, the prices that you see today for buying each asset has to be given by some non-negative combination of the payoffs for the future states of nature. Okay, where this Q will be an implied price basically. Okay. Okay. Fine. Okay, so let me move on. If you've got questions, we can discuss this again. Okay, but I do want to cover two more things before we complete today. Okay, okay. So two things I want to mention. So one, I want to do one more theorem, but before I do that, I won't be covering the dual simplex method. Okay, but I want to mention this. Okay, okay, because we will be using this potentially when we do sensitivity analysis, so I want to discuss the idea. The techniques of implementing the dual simplex are very similar to primal simplex with some caveats. So I'm not going to run through an example, but I just want to give you the big picture here. Okay. So think about what are we doing in LPs? We are solving this problem in primal LP, standard form. We start with a basic feasible solution, which is feasible. Okay. So this is primal feasible. And then what are we doing? We are trying to ensure every time in primal simplex that we are trying to move the reduced cost, make it non-negative, so that ultimately I get this reduced cost vector to be non-negative. Okay. For this primal LP, so we are basically going from primal feasibility, we are going towards the optimality. What is a dual problem for this? This is the dual problem is to maximize P transpose B subject to P transpose A less than equal to C transpose where P is free. Okay. This condition, if you interpret CB transpose B inverse as P transpose, okay, which is what we did, this is nothing but P transpose A is less than equal to C transpose. So this is a dual feasibility condition. Okay. So in a primal simplex method, we start with primal feasibility and work towards primal optimality, which is nothing but dual feasibility. In dual simplex, you're going to start with a dual feasible solution and work towards a primal feasible solution, which is basically dual optimality conditions. Okay. So you will essentially start with a simplex a tableau where the reduced cost vector will be non-negative. Okay. And then, but it will not be, so it will be optimizing every time in the primal simplex method, we are in this feasible region. In the dual simplex, we'll always be in this feasible region and we'll be working towards dual optimality, primal optimality. I'm sorry, dual optimality. Okay. So the way it's going to change is previously we would start with a variable, the entering variable with a negative reduced cost. Okay. So in dual simplex, when you have your simplex tableau, okay, in the tableau, your basic variables. So in the tableau is the same. Okay. You keep track of the same things in the dual simplex, except here one of these entries will be negative. Okay. So there'll be one of these entries which will be negative in dual simplex. So we're going to first identify the exiting variable, and then we are going to look at we're going to do a ratio test similar to primal simplex to find the entering variable. Okay. So instead of first finding the entering variable and then exiting variable, you're going to go in this direction. Okay. The I don't want to get into all the steps here. The book has it. It's not particularly hard to understand. Essentially, we're trying to make work towards primal feasibility, but this vector will be non-negative. So we're going to always do it so that this condition is always satisfied. We will never let this number will always be non-negative, the reduced cost vector. Okay. So we'll always maintain this condition, but we will work towards making these numbers non-negative. Okay. And again, we will talk about why sometimes, so the codes will implement both primal and dual simplex. Sometimes primal simplex is faster, sometimes dual simplex is faster. And I'll tell you when you might use one over the other. Uh, you don't have to go through all the steps again, but you can do it at your own time. You can look at the book if you want. Okay. But that is an implementation of simplex in the dual space. Okay. Okay. Any questions there at the high level? Okay. Okay. So I want to end with one last application of duality, which I think again is very important. Okay, which is basically representation of polyhedron and polytopes. Okay, I'm going to show the result only for polytopes. I'm going to prove it only for polytopes, but that is a similar result for polyhedron. Okay, again, this is a very important idea, and I want to just ensure we get this idea clear. Okay, okay. So here's the theorem. Okay, again, it's a very very uh, uh, useful point, and so hopefully we can understand this. Okay, so let's say P is given by x in Rn, Ax greater than equal to B, and I'm going to assume for this theorem that, I mean, of course, I'm going to assume it's non-empty, but I'm also going to assume it's a polytope. Okay, which means it's bounded. Okay, if it is unbounded, there's a similar result. I can tell you the result, but I won't prove it here in the class. Okay, the book has a proof also for the unbounded case. Okay, so let's say you've got a non-empty polytope. Okay, then, and let Q be a different set written in the following form. Where x1 up to xk are extreme points of P, of the set P. Okay, the theorem says P and Q are the same. Okay, so let's first understand what the theorem is trying to say, and then I'll prove this very quickly. Okay, okay. So what is a polyhedron? So a polyhedron is basically, the way I've defined it is by a set of, I take constraints, either inequalities or equalities, it doesn't matter. I intersect them. Okay. If it's equality, I can write it as two inequalities. So I can write any polyhedron in this form. Okay. For this theorem, the way I'm going to prove, I'm only going to prove the polytope case. So this set is non-empty and it's bounded. Okay. So because it's non-empty and because it's a polytope, we already know that there will be extreme points for this set. Okay. Let's say I enumerate all the extreme points. There are only a finite number of them, x1 up to xk. I take the set P, I write down all the extreme points. Okay, we have shown that every non-empty polytope has to have an extreme point. Okay. Take any point which is given as a convex combination of the extreme points. The claim is that these two sets are the same. Okay. This representation, the P representation, is called a H representation. What does H stand for? Half space. Q is called a V representation. What does V stand for? Vertices. So you can write a polyhedron or so in this case, a polytope, either as the intersection of a finite number of half spaces or as the convex combination of a number of extreme points. Okay. Either representation is equivalent. This is useful because many times you will either work with this representation or this representation. Okay. So maybe just from a figure, suppose I give you three constraints. Okay. This is the intersection of three inequality constraints. I claim that if this is P, if I take these three extreme points and I write down the convex combination of these extreme points, it's exactly the same set. The convex combination of these 3 points is exactly the same set. So P and Q are the same. Sometimes you will work with the half space representation. Sometimes you will work with the extreme point representation. Okay. Is the theorem clear? Okay. It's not a trivial theorem. Okay. And I'll tell you why it's not trivial, but let's just prove this maybe quickly. Okay. So proof Okay. So one, so first we'll argue that Q is a subset of P. Okay. Is the theorem clear? The statement of the theorem? Okay. So step one, prove that the vertex representation is a subset of the half space representation. Okay. Why is this the case? So take any, so consider any x in the vector set in the Q. It can be written as a convex combination of these points. Okay. Okay. Now, if you take, you want to check, you want to prove that if a vector, if a point is in Q, it lies in the set P. That means you have to prove that you have to prove that AX is greater than equal to B when X satisfies these conditions. Okay. So let's look at what AX is. X can be written as a convex combination of the extreme points. Okay. So just plug in X as summation K going from 1 up to K, lambda K, XK. Because X is in Q, there exists such a lambda. Okay. Now I simply take the lambdas out, move the A in. Okay. What do I know about lambda K? It's non-negative. Xk is an extreme point of P. That means Xk's lie in the set. So I know that each AXK is greater than equal to B. It's an extreme point of this set, so it has to lie in the set. Okay. So this is greater than equal to B. This is non-negative numbers. So this clearly has to be greater than equal to. But I also know that the lambda k's are a convex combination. This is equal to 1. They add up to 1. So this should be equal to B, which implies, therefore, X lies in the set P because X started in the set Q. Each extreme point satisfies AX less than equal to B, AXK greater than equal to B. So AX has to be greater than equal to B, which means that X lies in P. Okay. So this is straightforward. Okay. The second part, which is to prove that Q is P is a subset of Q. Okay. Requires a use of duality. Okay. So now I want to argue that if I take a point in the set P, it lies in the set Q. Okay. So we'll do this by contradiction. Okay. So any point in the set will lie in the set. Okay. So suppose X is in P. Okay. So I'm going to prove, suppose P is not a subset of Q. Okay. Then because P is non-empty, okay, then there exists some X which is in P. P is not a subset of Q, right? And P is non-empty. There exists some X in P, but X is not in Q. This is what, so I'm going to prove by contradiction. Okay. If P is not a subset of Q and P is non-empty, I can find some point in the set P which doesn't lie in the set Q. That's my, because of this assumption. Okay. Okay. So we're now going to play the same game, create a LP. Okay. So create the LP of the following type, maximize. So this is similar to the trick we played for Farkas lemma. So I'm going to try to write this vector X as a convex combination of these points X case. Okay. So I want to maximize 0 subject to, so X is given to me. So I'm going to try to write X as a convex combination of all these points. Okay. Just give me a couple of minutes. We'll end with the proof. Okay. So what is this LP? Here I'm given X. I'm trying to write X as a convex combination of all the XK points. So XK is given to me. I'm going to try to find lambdas so that X can be written as a convex combination of these points. Okay. Okay. So the dual of this LP, so you can create a dual LP. Okay. So let me just take this LP to the next page. So you'll see we are going to play a similar trick like Farkas lemma. Okay. So this is the primal LP. Let's call this P. So what's the dual form? Minimize P transpose X. So there's a dual vector here. And there's one equality condition here. So there's a scalar here. So P transpose X plus Q subject to P transpose XK plus 1, which is plus Q. Compare this to 0. This should be greater than or equal to 0 for all K going from 1 up to capital K. So that's a primal, that's a dual. Okay. Okay. So what have we assumed? We have assumed at this point that there exists some X in P, but X is not in Q. Okay. So when I try to write X as a convex combination of these points, X doesn't lie in the set. So that means under my assumption, primal is infeasible because X is not in, because X, since X is not in Q, I cannot write X in this set. I cannot find lambdas to satisfy these conditions. Okay. If primal is infeasible, then dual is either infeasible or unbounded. Similar to what we did for Farcas lemma, it's either infeasible or unbounded, but it cannot be infeasible. Why? Because I can put P and Q equal to 0. Okay. But the dual is feasible since P equal to 0, the 0 vector, and Q equal to 0 will always satisfy this condition. So therefore, the dual is unbounded. Okay. So same game like Farcas lemma. Okay. What does it mean for this to be unbounded? This condition has to be greater than or equal to 0, and I can make this number go less than 0, essentially. And I can keep scaling my P's and Q's. Okay. So which means that, therefore, there exists P in Rm, there exists a P dimensions and Q such that P transpose xk plus Q is non-negative for every k. Okay. So each of this is non-negative, and this number is strictly negative. And P transpose X plus Q is strictly negative, because then I can keep scaling. I can multiply P by lambda times P, Q by lambda times Q, where lambda is non-negative, ensure this condition is satisfied, and move this value down to minus infinity. This is unboundedness. Okay. Okay. Together, what does this mean? P transpose XK is greater than minus Q, but minus Q is lesser than, if I move this side, P transpose X. Okay. So this implies, therefore, P transpose XK is greater than is strictly greater than P transpose X for every K. Okay. So you can find me a P vector so that for this point X, which was in the set P but not in Q, I can make this P transpose X strictly lesser than the values for each extreme point. Okay. So now we're going to create a contradiction. So consider this P. Consider this P. Consider this P. So there exists some P. So consider this P and form the LP. Minimize P transpose Y subject to the original conditions of the LP. Okay. Okay. So what do we know about this? The optimal solution for this problem has to be an extreme point. Okay. So optimal solution is at an extreme point. Okay. And X lies in this. So what do we know from this? Essentially, we know that P transpose Y has to be less than or equal to Sorry, let me P transpose Y. Yes, short on time. Shall we complete this next time? Or you guys can you sit for the proof for a few more minutes, or shall we can we finish it off? Okay, okay. So let me just finish this off. So let's move this to the next page. Just give me 5 more minutes. Sorry, I'm going overboard today, but it's fine. Yeah. So consider this LP. We form the LP minimum. So we know that the optimal solution for this is one of the extreme points, which is basically either x1 up to xk. Okay. 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 So let's say is at an extreme point. So let's say it is at xk. Okay. So what do I know? I know that P transpose Y is greater than equal to P transpose xk for every Y in this original set. Okay. In this original set, capital P. Okay. Don't get confused between the capital P and small p. Capital P is this set. Okay. Okay. So what am I doing here? I'm just saying that you take this P vector that you found and you look at one of the optimal solutions is at one of the extreme points. Let's call that xk. Then clearly for every feasible solution has to be greater than equal to the value at this point. Okay. But remember, P transpose the x vector. Okay. But look at this condition. Okay. But this contradicts the fact that P transpose X is greater than P equal to K, because remember X lies in the set P. Huh? X lies in the set P. So X lies in the set. This is a contradiction, right? This says P transpose X is in the set. So P transpose X is greater than equal to P transpose some XK. But this says all P transpose XK has to be greater than P transpose X. So together, this is a contradiction. Okay. This gives a contradiction. Okay. Which means that you cannot have a vector X which is in P but not in Q. Okay. Hence, you cannot have a vector which is X in P but not in Q. So P has to be a subset of Q. So Q is a subset of P. P is a subset of Q, which means P is equal to Q. Okay. 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 So I think we'll stop here. You can internalize it. Next week, what I'll do is so we have covered duality. Again, you'll require to just spend some time looking through it at your own time. Okay. Next week, I will spend discussing a bit about sensitivity analysis and large scale optimization. So, what happens when you have big size problems? What are some of the things you can do? Okay. And we will discuss that next class. Okay. Okay. Let's stop for today. Thank you.